Hi everybody, thanks for joining us today. My name's Tom Bradley from NVIDIA, and with me today is John Linford from ARM. And together we're talking about HPC application development on the ARM platform with NVIDIA A100 GPUs.
Yeah, thanks, Tom. So I'm really glad to be here with NVIDIA. ARM has been gaining momentum in HPC for a long time now, and the recent announcements from NVIDIA with the Grace platform and support for CUDA on ARM really just show how this, I think, is the next wave in computing for the ARM platform as far as HPC is concerned. One of the things that makes working at ARM interesting is that what we do as an IP company is essentially define a standard, a common platform that runs on all kinds of HPC class CPUs, everything from the A64FX to the Ampere Altra to the Thunder X2 that you find in the Astra supercomputer. All of these CPUs are based on the same HPC platform. And because the platform is built to the standard, the ARM platform standard, you can count on all the parts of the HPC software stack just working out of the box. So whether it's an NVIDIA platform or a Fujitsu platform or what have you, your compilers, your libraries, your file systems, MPI implementations, all the way up to your applications and debuggers and profilers, that all works out of the box. And you can just count on it without having to wonder. In many cases, you won't even realize you're on an ARM platform, or if you change CPUs, you probably won't even notice. It's the only thing you'll notice really is the unique features that come with the platform. And we'll talk about a few of those coming up in the NVIDIA Dev Kit here in a minute. Because we have this common platform that's stable and performant, we have a really rich and growing application ecosystem. You see in more and more things like containers on the NVIDIA NGC platform are multi-arch, and they're supporting ARM as well as x86. Applications from the public computing domain, including diverse applications like genomics, which is a workflow typically that involves many different stages, completely supported here because, again, you can just count on the compilers and all the supporting parts working out of the box. And this is true even for commercial applications. So it's been a very fruitful collaboration across all of our partners, and we're seeing a lot of great momentum here.
So the focus of this talk is on HPC application development on ARM. And NVIDIA recently announced the NVIDIA ARM HPC Development Kit at our GPU Technology Conference, which was back in April. So this dev kit is a hardware and software platform for both HPC and AI application development. It will be available in late July. And if you do want to find out more information about the system, or if you want to register your interest, then please use this link, which I'll show again at the end. At its core, the system includes an Ampere Altra Q8030 CPU with 512 gigabytes of DRAM, and it's connected through PCI Express Gen 4 to two NVIDIA A100s, each with 40 gigabytes of RAM, and the Bluefield DPU, which provides 200 gigabit InfiniBand interconnect. The A100 GPU offers nearly 10 teraflops of double precision, or 20 teraflops when you're using the tensor cores for matrix operations. And as I said, each of these GPUs has its own 40 gigabytes of HBM memory, which gives just over 1.5 terabytes per second of memory bandwidth. And it's connected to the CPU with the PCIe Gen 4. So for workloads which benefit from partitioning the GPU for smaller jobs or subtasks, such as ensemble members, we can also partition the A100 using multi-instance GPU, or MIG, which allows us to allocate computer bandwidth to different processes. And since this is a developer kit, it makes sense to also talk about how developers would program the system. Obviously, if an API, a library API exists, then we should be using that. It provides us with great performance and drop-in ease of use. But if the API doesn't exist, then the inflexibility of the libraries means we need to look at some other approach. So before CUDA was released back in 2007, there were a community of motivated developers who were using languages like OpenGL or DirectX to manipulate the GPU into doing scientific computations. But that was really quite complex and quite limited. So when CUDA was released in 2007, it massively increased our developer productivity. And that's what's shown on the right here. That's the platform specialized approach using CUDA C++. But in the 2010s, NVIDIA partnered with several people from the community to develop the first directive-based approach for accelerated computing with OpenACC shown in the middle. And this allows us to write in C++ or Fortran and add the directives in a way that is exposing the parallelism and exposing the data locality. It's portable to multi-core CPUs and GPUs, and of course, because pragmas are treated as comments if the compiler doesn't understand them, it means that it can even work on with compilers and platforms that don't understand OpenACC. But still, we wanted to be able to reach a point where developers could write in a single language and still get portable performance. And so in 2020, we released the first compiler allowing developers to write in C++ or Fortran, standard C++ or Fortran, and have that compile either to CPUs or GPUs. Now, with these standard languages, there are obviously still some gaps in the languages, and we can fill those gaps either with directives in the middle or CUDA C++ on the right, because all of these are interoperable. So the HPC SDK combines all of these approaches into a single product. It's a comprehensive suite of compilers and libraries and tools, and it targets the full NVIDIA platform, including the CPU, the GPU, and the interconnect. The HPC SDK supports all of the approaches that we showed on the previous slide, from automatic acceleration in standard C++ and Fortran, through directives and to custom CUDA code. And as well as the CUDA C, C++, and Fortran compilers shown here, the SDK also provides a set of libraries, both from the core algorithms that you can see in the middle there, through to linear algebra with cuBLAS, cuTensor, and so on. It provides communication libraries for scaling to multiple GPUs or to multiple nodes, as well as profilers, both for systems and compute level, kernel level, and debuggers through CUDA GDB for both host and device. And it's available for free, and it's released about 7 or 8 times a year. When it comes to ARM, the SDK currently supports Ubuntu, SLES, and Red Hat. And shown on this chart, you can see that most of the SDK, including all of the compilers for both CPU and GPU, the core and math libraries, and the communication libraries, are already supported on ARM. And we are working on those gaps there to try and have full support for ARM in the near future from all of the platform. Okay, back to you, John, to talk about the platforms.
Yeah, so to get a sense for the kind of performance we can expect from one of these NVIDIA, for one of these combinations of a ARM-hosted GPU and the A100, we took a look at 2 configurations. So we have dual A100 GPUs over PCIe, either hosted by the Ampere Altra Q80-30 CPU or the AMD EPYC 7742 CPU. And the reason we're looking at these 2 CPUs is they're really very comparable. They have similar power consumption. They have exactly the same bandwidth out to main memory. The key differences between them are that the EPYC has a higher theoretical double precision floating point peak at a theoretical max of about 3.5 teraflops, while the Ultra's theoretical max is closer to about 2 teraflops. And the Ultra provides twice as much L1 and L2 per core as the AMD EPYC. Now, there's a couple of nuances here. For one thing, the theoretical floating point peak in both of these chips is the number you're guaranteed not to exceed, and that's especially true on the EPYC. We found I can't find a case where anyone's scoring much higher than 2.5 teraflops on this chip. The Ultra, you do get a little bit closer to that theoretical peak, but again, you're not going to completely to hit it. But as you'll see in a moment, the differences in the caches do tend to factor into the application performance a little more dramatically. Another way to look at these chips is through third-party benchmarks. Don't just take it from me. Actually, go look at some of the numbers that have been published by AnandTech, and you'll see that in a common benchmark like SPEC, these CPUs really go head-to-head. So if you look at the SPEC int performance or the SPEC int FP performance of a single thread, the Ultra and the EPYC are about the same, with the Ultra slightly ahead on SPEC int and slightly behind on SPEC FP. But the Ultra has 80 cores. So if you take this out to a single socket performance benchmark, then the SPEC int performance of the Ultra is well ahead of, for example, the Intel Xeon, and is slightly ahead of the EPYC. The SPEC FP performance of the 2 is pretty much a wash. So the Ultra is still slightly behind, But this really underscores the fact that that theoretical floating point peak is not really a meaningful number when it comes to real world applications. The real world performance, as sort of measured by spec FP, shows that these chips are largely about the same performance. So to take this a step farther than just spec, we wanted to look at real HPC applications actually executing on the CPU and the GPU and a combination of the two, and really compare their performance in what would be a representative benchmark for HPC users. And in this case, we are taking a sort of out-of-box approach. So we're using either the GCC 10.2 compiler or the ARM compiler for Linux, or the NVIDIA HPC SDK21.2 as appropriate. Generally, we just run with whatever compiler is the best choice for that application, or if there's multiple choices, we tend to go with the one that gives you the best answer. Compiler flags, we try to optimize for the target CPU using mcube equals native or neoverse n1 as necessary, with as much optimization as we could do on the CPU side, and using appropriate math libraries as well. To run these, we looked at different kinds of parallelizations, including with OpenMPI or a combination of MPI and OpenMP. Some of the applications run on CentOS 8.2, some of them were on Ubuntu 20.4.
So we ran a spectrum of applications and benchmarks spanning various scientific domains. And many of these, in particular the molecular dynamics, physics, and seismic applications, are GPU accelerated, by which I mean the GPU dominates the critical path. Some of them have a mixture of CPU and GPU dominated components, like some of the quantum chemistry and the climate and weather applications, and some of the CFD applications. And some of them are CPU only. So the purpose of the experiment was to understand and to show the readiness of the platform for HPC application development. So even though most of these are GPU accelerated, we did also run them on CPU only as well as GPU to give us more experience with the platforms and to get a clearer picture of the performance comparison. This first chart compares the performance when we're running with the GPUs on ARM versus GPUs on x86. Greater than 1x here means that the ARM system gave higher performance. And what we can see is that the majority of GPU applications see very similar performance with the ARM CPU versus the x86 CPU, typically within 5%. And we'll come back and look at some of the outliers in a moment or two. When we compare the same applications, or most of the same applications on the CPU, as well as a few CPU-only applications, we do see a little bit more variability in the results, which is to be expected, really, because on the previous charts, the codes were running on the same GPUs, but here we're looking at quite different CPUs. And yet still, most benchmarks are within plus or minus 20%. Calling out some of the applications that have slightly lower performance on ARM, we see GROMACS, for instance, where the critical path is floating point bound. And we see about 80% of the EPIC performance, which is in line with the 32-bit floating point performance of the two CPUs. We also see Quantum Espresso, which spends about 2/3 of its time in the eigensolver in Scalar Pack, which is mostly ZGEM. And there we can see the 64-bit floating point difference. LAMPS is quite interesting because we ran a selection of test cases there. And some of those, like Leonard Jones and EAM, are benefiting from the larger AMD L3 cache compared with the Ultra, while others have smaller working sets, and they're actually fitting in the larger ARM L2 cache. So remember that the ARM has much larger, or double the size of L1 and L2, whereas the AMD EPIC has larger L3 compared with the ARM. So John, why don't you tell us a little bit more about NeMo?
Sure. So NeMo was one of the outliers where we saw dramatically better performance with the Ultra than with the EPIC. The bar chart here is absolute wall clock seconds, so lower is better. And we wanted to better understand what is causing this. NeMo is an ocean model, so it's mainly a memory-bound code. And we suspected that it had something to do with the higher L1 and L2 per core on the Ultra. So we took a look at this code using the MAP profiler from ARM Forge. MAP is a cross-platform profiler, so I can use the exact same tool on both the x86 and the ARM-based CPU, and take a look at hardware performance counters to get a sense for instructions per cycle, or how many L1, L2 cache misses, useful metrics about the performance of the code, and identify in what regions of code are spending the most time accessing L2 or main memory or so on. And what we saw was that the NeMo was showing a very low L2 data cache miss. In this case, only 7.5% of the accesses to L2 missed. And on further examination, we can see that that was a little bit higher on the EPIC. And this correlated really well with the performance we were seeing. So I think it really explained the performance delta. Essentially, NeMo has some sparsity of the structure, and all the data that you need to evolve the model fit very well in L1 and L2 on the Ultra. So we're getting some really good performance there. And it's not as limited by floating point performance as some of the other codes. So it can take more advantage of the L1 and L2. Another outlier we looked at was HiCom. HiCom performed better on the EPIC, but this is because this is an older code where the domain decomposition has been hard-coded for very precise numbers of MPI ranks. The Ultra Q80-30 is an 80-core CPU. In fact, the Ultra CPU lineup, the name of the CPU will tell you the number of cores and the core frequency. So a Q80-30 is 80 cores running at 3 gigahertz. When you have 80 cores, HiCom can only take advantage of 64 of them at best. And so what we saw is that if you're running the 64 cores of the Ultra, you're not taking full advantage of all the performance in the socket. But there are 64 cores in the EPIC, so you are in fact taking full advantage of that whole socket, and performance is a little bit better. If you compare something like the EPIC running at 46 cores to the Ultra running at 64 cores, so you're not using a full socket of either, performance evens out. But now I'm really reaching, I think, to make this comparison. A better comparison would be to run on the Ampere Altra Q6433, which is a 64-core socket running at 3.3 gigahertz. I think we'd see performance close a bit better there. It's also a lesson to application developers. Plan for high core counts, because if you hard code domain decompositions, the hardware is going to evolve. And so you're going to need to future-proof by being able to scale out to core counts that you might think are infeasible today, but tomorrow might seem very common.
We also looked at OpenFOAM. These two OpenFOAM benchmarks are both relatively large. One is 37 million cells and the other is 216 million cells. So like I said, they're quite large, and most of the memory accesses could be considered as streaming memory accesses, and the benchmarks are actually memory bound. Now, looking at the stream benchmark, which is the set of charts on the lower right-hand side here, we can see that the EPIC CPU, the x86 CPU, doesn't achieve maximum memory bandwidth unless we start using streaming stores. And what we see from the charts on the left, which is the application performance, we can see that the performance is consistent with that difference between not using streaming stores and what we would hope to see from the peak. For a real application, we could, of course, turn on streaming stores, but what we found is that enabling it for the whole application, or even on a per translation unit basis, resulted in slightly worse overall performance. And we didn't look at enabling it per store. And the main reason for that is that that would mean using intrinsics in our code. And the whole objective here was to run these applications without changing any of the code itself, only changing makefiles. Another outlier was CPTK. So CPTK here, again, the charts on the left are showing the speed up. And we can see that it was the blue ones are showing that the ARM plus the CPU only ARM was slightly slower, but the GPU accelerated ARM was 18% slower, so significantly slower. So to understand this, we need to note that CPTK performs a lot of small and unusually sized matrix multiply and accumulate operations. And on the CPU, CPTK uses a library called libxSMM, which has been highly tuned for x86 and a little bit less so for ARM. But nevertheless, the matrices are so small that the operations do tend to be bandwidth bound, and so we get fairly similar performance between the two CPUs. When we move to GPUs, on the other hand, these matrix multiplies are offloaded to the GPU, and we find that the PCI Express link from host to device becomes a bottleneck. And one interesting observation here, if you look at the chart on the lower right-hand side, you can see that the computational part of the code is pretty similar between ARM and EPIC. Its time on the vertical axis is so lower is better now, and it's slightly faster on the ARM versus on the EPYC system. But the orange part there, which is the communication, is significantly longer on the ARM system. And that's the communication across the PCI Express link. It's about 25% slower than we would expect. And we do also see this with the standalone bandwidth test. And so we're actively working on that in the runtime and the driver. And ultimately, we do expect that performance to converge. Back to you, John, then to talk about the process supporting to ARM.
Sure. So we took all these applications, we're running them on two platforms, x86 and ARM. And I'm often asked, how hard is that? I keep asserting that everything just works out of the box. So really, is there anything more to that? The answer is no. I mean, really, it doesn't. It does work out of the box, but there's a great process you can follow for quickly getting your application up and running on an ARM-based platform. The first thing you should do in all cases is check if the work has already been done for you. At this point, there's a lot of momentum for ARM in the HPC community, and that means a lot of applications have already been ported, tuned, containerized, and made available for you. So in many cases, it's as simple as downloading and using an existing container. The NVIDIA GPU Cloud, NGC, is a great place to start for this. It maintains a catalog of optimized and portable containers, including deep learning frameworks and models that you can use to get started very quickly, almost on any ARM platform out there, and certainly on any ARM platform with the Ultra and a A100 like we're showing here. Another great place to start is ARM's own HPC application wiki, which I'm showing the link here below. It will give you recipes and instructions on how to compile applications for ARM CPUs. So you don't get binaries there, but you do get the optimized, all the work has been done for you, recipe for building the application. Now, if you are quite certain that nobody has done this work for you already, and you will need to recompile the code, that's usually all that's required to move an application from x86 to ARM. Grab a good compiler like the NVIDIA compiler, ARM compiler for Linux, or any GCC that's newer than 10.2, and you should get very well-optimized performant code for any core based on the N1, like the Ampere Altra or AWS Graviton 2. Just build your code. It should work. Then you can run it. You will have to adjust for higher thread counts or higher core counts, like we saw with HiCom. The Ampere Altra has got 80 cores. Other ARM-based platforms out there are going to 128 cores now. You will have to rethink your domain decomposition just to take advantage of all that parallelism, but it's not that hard. You can do it. And then finally, after you've run the code, you can optimize it by using a profiler. Take a look at what you're seeing from NVIDIA Insight or maybe ARM Forge to find hotspots and focus on optimizing in those hotspots. Usually around this point, this is where I start getting emails from concerned users because they're getting differences in their floating point answer on the ARM platform than they were from the x86. ARM uses exactly the same IEEE standards for floating point. The fact is ARM's floating point is just as accurate as any other architectures, or put another way, floating point answers are wrong equally on all platforms. So usually what you need to do is take a closer look at your unit tests and use epsilon compares or something like that when checking floating point values. Thankfully, a lot of people do this already, but it still crops up. If you see floating point regression tests failing on ARM, just go check that you haven't encoded any hard values there that were in fact calculated on x86. I should mention that ARM does have a suite of developer tools, very like the NVIDIA HPC SDK, although less featureful. This is a combination of compilers and profilers and debuggers called the ARM Studio. You can find it on ARM's website. It's a great addition to the existing software stacks that ship with the NVIDIA HPC SDK.
And complementing the ARM tool chain that you saw there, we have the NVIDIA HPC SDK. The first version of this was released in last year, and it was version 20.5, so May last year. And even then, the compilers and libraries fully supported the ARM server CPUs, and that's with auto vectorization, vector intrinsics, and all of the programming models that I described at the beginning, from ISO standard languages, OpenACC and OpenMP, and CUDA. And as we continue to work on the ARM platform, we will see the rest of the NVIDIA HPC SDK, including Rapids and the DL frameworks, maturing for the ARM platform as well. And finally, to summarize then, the NVIDIA ARM HPC Dev Kit is It's a validated system which has been designed for development, bring up, and analysis of accelerated HPC and AI codes on the NVIDIA GPU with the ARM CPU together in one platform. So for more information, please do register your interest at the link here. And with that, thank you very much from both of us.